The last part was about the property of inductance, and we now come to another property of electrical components called capacitance. You'll remember that when we were thinking about inductance, we saw that any change in current in a circuit, and thus in the magnetic field, is opposed by inductance. We shall now be dealing with the property of components which oppose any change in voltage. They try to hold down a rising voltage, and they try to hold up a falling one. This property of opposing voltage change is called capacitance, and the components designed to provide capacitance are called capacitors. As we shall see, they can store an electric charge. Often you may hear them called condensers instead of capacitors. They're the same thing. The principle of a capacitor is very simple. It consists of two conducting plates parallel to each other but not touching. They are separated by an insulator, which in this case is the air between them. When they are connected to a source of supply, a battery say, they behave as a very simple capacitor. So let's see what's happening. Here are the two plates separated by air. The material between the plates, whatever it is called the dielectric. Now when the switch is made, electrons flow from the negative terminal of the battery onto the plate connected to it, making the plate negatively charged. At the same time, electrons are drawn away from the other plate onto the positive terminal of the battery, leaving the plate positively charged. Eventually, the flows will stop when the potential difference between the plates is the same as the voltage applied by the battery. The capacitor is now said to be charged. If the switch is now broken, the charge remains on the plates and the capacitor is storing an electric charge. When charged like this, the capacitor is rather like an electric cell with a positive and negative terminal, and in fact it will behave like one for a short time. Suppose this charged capacitor is now connected through a switch to a lamp. On closing the switch, current will flow for a short time, lighting the lamp, as the electrons rush round the circuit to the positive plate. The flow stops when the electrons have neutralized the positive charge on the positive plate, so that the potential difference between the plates has disappeared. The capacitor is now said to be discharged. In real life, this is easy to demonstrate. Here is a capacitor connected through a switch to a power source. By closing the switch, we charge the capacitor. When we break the switch, the charge remains in the capacitor, as we can easily show. Watch. Incidentally, notice that the screwdriver used to discharge the capacitor has an insulated handle. It's an essential rule never to discharge a capacitor when it is still connected to a battery or the mains. Now this capacitor was very simple. It would not be very good at storing a charge. Its capacitance is low. It can be improved in a number of ways because capacitance depends on three factors. First, the area of the plates. The larger the plates, the greater the capacitance, the more charge that would be stored. Next, the distance between the plates affects capacitance. The closer they are together, the greater the capacitance. And finally, the dielectric. Here it's air, but if a better dielectric is used, more charge could be stored. The capacitance would be greater. Typical dielectric materials in addition to air are mica, glass, and waxed paper. So the ability of a capacitor to store charge, its capacitance, depends on the area of the plates, the distance they're apart, and the dielectric between them. There are many types of capacitors and a wide variety of shapes, sizes, and capacitances. But those met with are usually of two types, the paper capacitors and the electrolytic capacitors. Paper capacitors take their name from the material of the dielectric. If we take a capacitor to pieces, we find that it consists of two strips of metal foil with leads attached. These are the plates. with a strip of waxed paper between them to form the dielectric. Further strips of waxed paper inside and outside act as insulation. The whole thing is rolled up into a cartridge and sealed with wax into an outer case. Large paper capacitors are usually sealed into metal containers. When paper capacitors become inconveniently large, electrolytic capacitors are used. Here the dielectric is a thin film of oxide on one plate. The capacitor must be connected with the terminal with the red end or spot to the positive side of a DC supply. As with the paper capacitors, there's a great range of shapes and sizes of electrolytic capacitors. When drawing circuit diagrams, the symbol used for a capacitor is this. And capacitance is measured with a unit called the farad, capital F. But a capacitance of 1 farad is enormous. We are much more likely to come across millionths of a farad, which of course are called microfarads, written like this. So now to sum up what we've seen about capacitance. Capacitors are electrical components of a circuit which can store electric charges by becoming charged. You will come across many capacitors, mostly of 2 types, paper capacitors and electrolytic capacitors. Here are some examples. In the next part, we shall be looking at the various pieces of electrical equipment which are essential to the subject of electrical engineering.